The delta H of a reaction is equal to the sum of the delta H values of any reaction that, when combined, equal the overall reaction. That's a really good definition, but it makes me say, huh? And that science speak definition will make sense by the end of today for you guys too. But right now, it's definitely, huh? So in plain English, this means that reactions, like regular algebraic equations, can be combined into one large equation. When we do this, we add the delta H values for the equations to get the total delta H for the combined reaction. And if you're like me, you're like, yeah, I kind of like puzzles. Puzzles are fun. You can do puzzles. But why are we doing this? Well, the reason that we are doing this is because in the lab, there are certain reactions that we cannot safely do. But we still want to know information about those reactions. And we can do other reactions that are similar to that reaction that we can then combine algebraically to figure out what the delta H would be for an equation that, or for a reaction that we cannot actually do in the lab. So this is keeping us safe. It's another way of saying it. Let's do an example. So our first example, we have these two equations. SO3 plus H2O goes to H2SO4, and SO3 plus BaO goes to BaSO4. I can combine those. I can add it all together. The reactants all get added together with the reactants. The products all get added with the products. And I write it in one big long equation. Reactants on one side, products on the other. So I get BaO plus 2SO3 because I had SO3 in both of the reactions. I had 1 mole of SO3 in the first one, 1 mole of SO3 in the second one. Added together, 2 moles of SO3 plus H2O gives me H2SO4 plus BaSO4. Well, what I'm really looking for is a value. So I'm going to add together the delta H values. And I get negative 75 plus a negative 82 gives me negative 157 kilojoules. Yeah, Duncan.
So does this law assume that if you do two reactions at the same time together, the outcome will be the same? Or are these two separate reactions?
Two separate reactions.
And you're just saying the total energy of the two reactions
would be this. Exactly. Exactly. Because for some reason, the combined one that we have there would not be safe for us to do. Or not be reasonable for us to do. But, so, I'm good that you're thinking that, because it's not always this straightforward. Because doing the equations just for the sake of combining equations would be pretty pointless. It'd be silly. So what we do is we use Hess's law when we have a target equation in mind. I have some equation that I would love to do in the lab, but I can't for whatever reason. Maybe it's I just don't have enough time. But I can't do it, But there is some data, and I'm going to use that data to figure out what it would be. So let's see an example that's a little bit more like what you're going to see on your homework and quizzes and tests. So what I want to know is how I can combine the first two equations to get to my target equation. So I have an equation, first one, SO3 plus H2O goes to H2SO4. And that has an enthalpy value that's negative 75, so that's an exothermic reaction. I also have SO3 combining and reacting with BaO to form barium sulfate. Nice synthesis reaction there as well. The delta H is negative, it's exothermic, negative 82 kilojoules. To get that reaction at the bottom, H2SO4 plus BaO gives me BaSO4 plus H2O. Can I do it like I did the last time and just put the things together? No. Because I have H2SO4 on the wrong side. I have it on the product side in my beginning equations. I want it on the reactant side. I also have those two SO3s that don't show up anywhere in the target equation. So here's where it becomes a puzzle. We can manipulate the original equations in the following ways. We can multiply the equations to get a number of moles that we want. We could divide the equation by a number of moles that we want. And we can flip the reactants and the products. So that H2SO4 that was on the product side that I wanted on the reactant side, I can flip it. I can flip it all around. I don't just flip one thing, I flip the whole equation. So all of my reactants become products, all of my products become reactants. If I'm multiplying because I want 2 moles of something and I only have 1, I multiply the entire equation by 2. Not only do I multiply the whole thing or divide the whole thing or flip the whole thing, I also have to manipulate the delta H values. So, if I multiply by 2 all the way through, I also have to multiply the delta H value by 2. If I divide by something, I have to divide the delta H by that same thing. Here's the one that you'll need to memorize, and it ties us back to the notes that we did with 3-1 or 5-1. If we flip the reactants and the products, we change the sign of the delta H. And we said that in 5-1 when we were talking about reversible reactions. A reversible reaction going one way is endothermic, going the other way is exothermic. So if we flip around our reaction, products are now reactants, reactants are now products, the delta H, it's no longer exothermic if it was before, it's now endothermic, or vice versa. So we need to flip the sign. So let's look back at this equation. We want to get to H2SO4 on the reactant side. So we're going to flip that around. H2SO4 goes to SO3 plus H2O. My delta H is no longer negative 75, it is now positive 75 kilojoules. So when I flip it, the sign flips as well. So now I can put this all together. All of my reactants are going to go on the left side of the arrow. All of my products are going to go on the right side of my arrow. And I get H2SO4 plus SO3 plus BaO goes to BaSO4 plus SO3 plus H2O. Is that my target equation? No. What is different with this? The SO3s. Well, lucky for us, if we have the same thing on the reactant side that we have on the product side, they cancel out. So my SO3s are not really there. We'll rewrite this without the SO3s in it, and then I am at my target equation. H2SO4 plus BaO goes to BaSO4 plus H2O. Now I just have to do the part that actually gets me the answer that I want, which is what is the enthalpy for this reaction. I take my two values and I add them together. So I have my delta H for my first reaction was negative 75, now it's a positive 75. And I add that to my second enthalpy, which is negative 82. We didn't do anything to that equation, it's still just negative 82. And we get a final answer of negative 7 kilojoules. And that is what I would be looking for on a test or homework. Negative 7 kilojoules. That's really all I need. Duncan.
With this law, would you always be using a situation where you can assume that the outcome is already known, although you just necessarily can't test for it? Because if there's a reaction, you can't. I mean, with like the laws and things, you can assume what the outcome would be. But I feel like there's a lot of situations where this law wouldn't work.
Yeah, sometimes chemists do things in the theoretical world without actually being able to ever test if it actually works. And so sometimes we do these, even though they might not actually work in the real world. Good question. Maggie? Yes. Yep. Delta H's for the given equations would definitely be given to you. Good. Good. And I also had a question last hour. Will you ever have to go in the opposite direction? So if I gave you a delta H of a combined reaction, would you have to go backwards? No. Nope. It's always going to be this way. Go ahead, Emily.
Do you always do like the changing to the first reaction, or does it not really matter?
It doesn't really matter. We're just going to go to whatever gets us to the final equation that we want. Good question. And we'll see that in our next example. What other questions before we move on? Panera?
I'm kind of confused as to like, the whole point of this equation because it's the same one as like, the original.
On example 1?
Yeah, no, example 2. It goes back to the exact same equations.
It does, because that was the target one that we were looking for. We were just trying to figure out how to get there. Yep. Okay. So, example 3. We want to manipulate 3 equations this time to get to some value for my target equation. And my target equation this time is 2 carbons plus 3 hydrogens forming C2H6. That's what I want to get to. And I've got 3 equations that I can actually use to figure out what this value would be.
Wait, so you're going to give us that, or?
Yeah. Oh, yeah. Yeah. This whole thing right there would be given to you. Yep. You just have to figure out how to manipulate those 3 equations to get to the target one. So first thing I see is a 2C. Where do I have carbons? Which equations? 1, 2, or 3, or all of them, or 2 of them? Carbon on its own. Sorry, be more specific. Just in the first one. So the first one, the only one that has carbon on its own. And it says that I need 2 carbons. But how many carbons do I have in the first equation? 1. Is that carbon on the correct side? Yeah, it is. So I do not need to flip it, but I do need to multiply that entire thing by 2. So I'm going to multiply and get 2C plus 2O2 goes to 2CO2. We're going to worry about the enthalpies at the end. The next part of my target equation said that I needed how many moles of hydrogen? 3. Which equation has only hydrogen in it? The second one, yep. So I'm going to multiply that entire equation by 3. And I get 3 H2s plus 3 half O2s goes to 3 H2Os. And again, I'll multiply my delta H by 3 later on. It says that that whole thing forms C2H6. 1 mole of C2H6. What's wrong with my final equation there? It has 2 moles of C2H6. Anything else? It's on the wrong side, yeah, so I have to do 2 things to this one. I need to flip it and divide by 2 because I only need 1 mole of it, and I need that 1 mole to be on the opposite side. So my products are going to become my reactants, and there will be half the amount of moles of each of my substances. So 2 CO2 plus 3 H2O forms 1 C2H6 plus 7/2 of O2. Gotta love fractions. Okay, let's reduce this a little bit. So, just rewriting exactly what we wrote on the last slide, but figuring out what I have and what I can get rid of. First of all, I want to double check, make sure I have the things that I was actually looking for in the right places with the right amounts. And sure enough, I've got 2 carbons plus 3 H2s goes to C2H6. So all of the stuff that I wanted is there. But I want to see if I can get rid of all the things that I didn't want. So let's look here. I've got 2 CO2s on each side. So those cancel out. 2 CO2s on each side cancel out. My H2Os, I have 3 on each side, so those cancel out. Now is that pesky fraction. I have 7/2 on my product side. Do I have 7/2 on my reactant side? I do, yeah, because 2O2 is the same as 4/2 O2. 4/2 O2 plus 3/2 O2 is 7/2 O2, which is what I have on the other side. So that indeed does cancel out. So I have reached my target equation. I am left with 2C plus 3H2 forms C2H6. But I have not done yet what I actually need to do. I haven't figured out what I actually need to figure out yet, which is my delta H. So I'm going to look back at what I did to each of these equations and look at my delta H values and do the same thing to them. So my first equation, I multiplied by 2. And the delta H of my first equation was negative 393.5. So multiply that by 2, we get negative 787 kilojoules. My second equation, we did multiplied by 3. So I multiply the enthalpy of that reaction by 3. And I get negative 857.4 kilojoules. I did 2 things to my last equation. I flipped it and I divided by 2. So flipping it means my sign is going to change. It was negative originally. Now it is positive. I divided by 2, so I need to divide my number by 2. So it has gone from a negative 3119.6 to a positive 1559.8. Now all I have to do is add those numbers together, and my delta H of this equation that I couldn't actually do in the lab, or that I didn't have time to do in the lab and I had this other data, is negative 84.6 kilojoules. So it is still an exothermic reaction. What are we doing?